So hi everybody, today we're going to be talking about time series forecasting in Python using Statsmodels SARIMA seasonal ARIMA package with exogenous regressors. And here I'm actually showing the final result at the end of this video. We're forecasting historical sales of vehicles, that's in the blue curve, and we've held out an orange piece at the very end at the far right, that's the test set that we did not touch and we left on the side. We did all of our modeling using the blue data, and our green curve is actually our forecast. So you can see that we've done a pretty good job. And in this video, I'm going to show you how we achieved this result. This data comes from the Fed, St. Louis Fed, economic data. This is total vehicle sales, which is the series we're trying to forecast. And you can kind of see it's kind of steadily decreasing. In the middle, we have COVID, which kind of interrupts things, and then it has a different dynamic after. These series are very common in today's world, and this is hard to predict through, but that's why we're going to bring in GDP, which is a measure of the state of the total economy, and it also experiences a dip during COVID. So by using a series that measures the state of the economy like GDP, using it in a model that's trying to predict sales can help it explain the data through this point and then go off into the future. And you can get a pretty good result like this. So hopefully it's useful to you guys, and let's hop over to the video.
Hi everybody, today we're going to talk about ARIMA modeling in Python. And just to get started, let's import some libraries. We're going to import pandas, we're going to import numpy, we're going to import matplotlib. We're going to import deep copy, which is just a helper function, a helper method that helps us copy lists and objects and stuff like that. We're also going to import warnings, just because when the Statsmodels fitting fails, which happens often, we don't want to get a bunch of warnings to the screen. So action equals ignore. And then of course we want to import the actual modeling itself. SARIMAX, so it stands for seasonal autoregressive integrated moving average with exogenous regressors. So that's what we're going to end up using here. So we're going to go ahead and run this. Okay, cool. Now we're going to read in the data and visualize it. So let me just show you. I've got GDP and I've got totals, SA, CSV. So basically this is vehicle sales data over time, and GDP is GDP. It's gross domestic product for the US basically. And this is a vehicle sales for the whole country, essentially the whole US. So the idea is that can we forecast total vehicle sales and use GDP as sort of an exogenous regressor for that and see how well we could do that. So let's read in the data first. We're going to read in the sales data. Total, let's say, and let's just look at this monthly data. We got I think these are in millions or some index, but it's monthly. And we want to get the date parsed because we want Python to interpret the date correctly. So we got that. Now let's read in the GDP. GDP.csv. What does GDP look like? The GDP is actually quarterly. So you can see here it goes January, April, July, October, and it repeats. So it's quarterly data, and it's starting from basically the beginning of each quarter. So there's 4 quarters in the year. This is mapped to the first month of each quarter. So let's see what we do with that. But basically, this has a date. We want to parse that as a date as well, just because we want Python to be interpreting that correctly. And there we go. We got our data. I ran into an issue. I misspelt parse dates. So we're good on that. Next, we want to basically just visualize these two. So let's take a look at them. Let's do figure. Let's do PLT plot, sales, date, sales, and what's the name of this? Let me double check this guy. Total is a. Let's give that a nicer name. Let's go rename columns. Totals A. It's just sales. That's all it is. So it's just going to be called sales from now on. So let's do sales, label equals sales, TLT plot. Let's do GDP this time. GDP, label is GDP, of course. Let's go ahead and show that, and let's not forget the legend. Let's actually make this a little bit bigger. Okay, so we can see we got GDP in orange, sales in blue, but GDP in orange is drastically higher. So let's bring that down. We can just do that here by dividing GDP by some factor. Let's just use 1,000 and see what that looks like. So if I replot this, now they're on a better scale. So great, awesome. We can see that GDP extends a little bit earlier than our sales data. So there's a gap there. And also over here, GDP is not as current, and that's because GDP is quarterly. It's a quarterly number. So we're missing months here. So we're going to want to kind of get these two series on the same monthly grain. We've seen that GDP is quarterly and the sales is monthly, and we have these kind of edge effects. So we next have to basically just merge those two together somehow, and that's what we're going to do here. Okay, so let's try to get the GDP and sales data on the same grain. So if we look at these again, sales is monthly, GDP is quarterly. Now what I'd like to do is actually make these dates the center of each quarter and then merge it onto the sales data. So what I mean by that is, let's see, Q1 of 2022 is in January, February, and March, right? So instead of being represented by January, like here, 2018 January is where the value hits, I want to move it to the center of the quarter. So this is the whole quarter. I want it to be February, right? So if we look at Q2, for example, those would be the months April, May, June. And instead of being represented by April, as it is here, I want it to be May. I want it to be the center of each quarter. So let's look at the GDP. So obviously it's quarterly. Let's create a second date column that is going to be based on the first, but we're going to add 32 days to it. So now this moved the 4s to the 5s, the 7s to 8s, the 10s to 11s, which is exactly what we want, except we picked up these extra days, which is fine. What we're going to do is create another column called, it's going to be based on day 2, lambda x dot replace day equals 1. So what this will do is basically set the day to 1 for each of those months, and it does. So 7 gets moved to 8, but then we correct the day to be 1. So all these days are 1, and they all match up with this, which is perfect. So that's good. That's exactly what we want. So now let's persist this. So make it equal what GDP was before, and let's not have date 2, 3, 4. Let's just have one day column. So I'm going to replace these all with just date, and that should give us what we want. GDP. Okay, perfect. So we have 5, 8, 11, 2, 5, 8, 11. Exactly. So the center of each quarter, and we have the data for that on each, which is exactly what we wanted. Next, we are going to merge the sales data with GDP data, and let's see how that looks. So we merge them together. We have some NANs because GDP does not exist for all the months, just the center of each quarter. So that's your February's, was it February, March, August, and November. So for other ones, we missed it. We see the dates are kind of jumbled up, so let's just sort this by date ascending is true. So yeah, that's sorted there so we can see it better. So now we see, yes, we have the dates in order, we have sales data, but we're missing these gaps for GDP, right? So we can even look at like the tail, look at the tail 15. Last 15 observations, we have sales data, but we're missing GDP, right? It's missing. So let's impute the GDP that is missing. We're going to do that with the interpolate method. We're going to use linear, and we're going to limit the direction to backward. And let me show you why. So Panda's got its interpolate method. We're just going to use linear. Now GDP exists quarterly. It doesn't exist monthly. And for our purposes, it's perfectly fine to use linear interpolation because it's not a real value anyway. We just want it to exist for all the months. This is perfectly fine. So when I do this, you can see that we're missing, GDP values in between the months, right? Obviously. So if I run this, we get them all filled in perfectly. GDP is constantly increasing, which is what it generally does. Except in times of COVID, for example, early 2022, GDP took a dip, so did vehicle sales, and that correlation is what we're trying to help GDP get us through, essentially. So when you have series that have this annoying kind of perturbation, exogenous regressors can help with stuff like that. But anyway, if we come back down here, um, notice it did not impute the future kind of tail end values here. That's because of this limit direction backwards parameter. The reason is because if I just do without this, for example, it's going to make those values just strict 25 throughout the same exact value. It's going to pull it forward, but that's not true because GDP is constantly increasing, so this is not correct. So we're going to do something else for that. What we're going to do for that is get the growth rate for these last few months and apply it forward. That's what we're going to do. So what to do that is we're going to let me first just make a column for it. So it's going to be df divide by the prior value. So this allows us to divide the current value by the prior value. You can see the growth rates here. So if you look here, it's about 0.6, 0.6, 0.6, 0.5, 0.5. It's roughly 5 or 6, 0.5 or 6% growth rate month over month, and that's what we want to project forward. So let's just get this to a fixed number, growth rate. So we just want drop the NAs, and we want to get the last, say, 5, and we want to take the average. And then what we want to do is if our GDP value is null, meaning if it's one of these guys, as we iterate the rows of this, if it's one of these guys, we actually want the value to be equal to the prior value times the GDP average growth rate. So this again, it fills it in again, awesome. And now we have these future values filled in, and you can see they're steadily increasing at the growth rate, at this growth rate, which is exactly what we wanted. And so now, let's just visualize these guys again. Let's look at data frame again. We see we have these early sales NAs, which are caused by this gap back here. We don't really care about that, so we're just gonna go ahead and drop NAs here because we're not really concerned with that. We're gonna reset the index while we're at it. Now we don't have that issue, and now let's just go ahead and plot this stuff. So I'm gonna grab the code for plotting up here, come back down. Let's just plot this. So this is gonna be all data DF data frame. We have them both here, so we should be able to just graph this. And there we go. So we got everything perfectly lined up and stacked up. We have perfect one-to-one correlation. It's all monthly, so we're in a good position to go ahead and start modeling this out. Okay, so let's create the training and the test sets basically. So let's look at the tail of this again. Let's get the last 15. And I don't know, maybe around March or so is a good place to cut it into training and test. So let's do DF tail 7. So if we take the last 7, that gets us to March. So let's go ahead and use that as our date, a cutoff date. So our max training date, I'll set it to that. So let's just create a quick figure here. This time I'm going to drop in this line, red line style, just to like delineate basically. So forward of the red line is our test set, and behind that is our training set. So the idea is we want to use all of the training, so everything behind the red line, to predict, to build a model, do everything we can to build a good model, and then use that to predict the future. So after the red line, and that's the main idea. So let's go ahead and create the training data set. Look, df8. We're going to take that to just be the max, like that. And the test set is going to be like this. Max training date may be a bit of a misnomer. It's just a separation date. That's less than or equal to whatever. It doesn't matter. It's basically just partitioning the two sets like that. So let's hit that. And we're good. So now we're going to hop over to just go ahead and build a model. So let's just manually specify a model and see what it looks like. So we're going to use the training data sales. So the endogenous value is the series itself. So that's the sales data. Our exogenous regressor is GDP, of course. Now we have to specify the order parameters. So let's just call it 113 or something. So this is your PDQ order parameters for ARIMA. And let's go. We have our we have trend parameters, which I'll describe in a minute. So this is like the A of t function, which is something like A0 plus A1 times t plus A2 times t squared and so on. This controls the time dependence trend. Then you got your seasonal parameters, which I'll just set to be like 100, and you have to specify the frequency or the seasonality of the model, which is 12 monthly for us. So that's what that 12 is. So don't get thrown by that. But the seasonal order parameters are this. They're P, capital D, capital Q. So they kind of fall in line with the ordinary ones you may be familiar with. Okay, so this is the model. So you get these objects. Most people you'll see do something like this. They will define fitted model equals model dot fit, and then they'll do something like this summary. So the fitted model is what you actually interact with. So you get the regression summary here. I'm going to skip all that, and I'm just going to call fit directly. So that way we can work with model methods directly, basically. So let's see. Now what we want for here is basically to see the forecast. So forecast of this, we can use the forecast method, and it requires a number of steps. So the number of steps is going to be equal to the test set's length. That's how many steps we need to forecast. And the exogenous regressor is just the test set for GDP, which makes perfect sense. And now let's go ahead and plot this. So we're going to plot this guy. We're going to plot DLT, training data set, train sales. And this is our historical sales. Then we're also going to plot the test. And this is our future sales. And these are like the actuals. And then we're going to go ahead and plot the forecast from the model. Let's call it future sales forecast, and this is actuals. Let's see how this looks. And let's just make this a little bigger. Size. Sorry. Okay, perfect. So We got our blue historical, our orange actuals future, and our future sales forecast. You can see that's pretty bad actually. It's just flying off to the side. I wonder if we change this a little bit. What if we set that to 1? Kind of brought it down a little bit. Interesting. What if we got rid of this guy here? Got a totally different forecast, which is interesting. So the point is that this playing with the order parameters of the ARIMA model, or the so-called hyperparameters, if you're talking machine learning speak, basically determines the forecast, and so does the data, of course. But really, the magic of this sort of tutorial I'm showing you today is how are we going to select the hyperparameters for this model, because that basically determines what the forecast is going to look like. And the idea is that we only want to use the blue data to predict the orange data. We are not going to touch the orange data at all. Right, so that's the main idea of what we're trying to achieve here. Okay, so let's start seeing how we're going to go about selecting the order, trend, and seasonal order parameters of the ARIMA model. So what we're going to do is create a scoring function and a search function to basically search the hyperparameter space and score different hyperparameter combinations to find the best one. Now, before I start writing that, let me show you what I'm going to end up doing. So imagine we've got an optimization loop. And what we're going to do basically is say something like, here's our initial guess. Let's see, P, E, Q, capital P, capital D, capital Q, A0, A1. So what these all are the parameters that would be used in the definition of an ARIMA model. So we got the lowercase pdq, the uppercase pdq, and then these a terms basically here. So basically we would define that, and then we would have a way to score it. So x0 basically holds the place of a parameter combo, and then f0 would be like a score method on this to see how good is this combination, how good is it. And then what we would do down here is basically say, well, starting from this point, what if we randomly changed x0? So what if we did a random step from x0 to get to x1? And then what if we scored x1? And then what if we checked if f1 was smaller than f0? In other words, if the new point is lower in score than the previous, meaning better, if we move to a better point because the score is improved, and for us score is error and lower error is better, then we're actually going to update our probe to be that exact value. So we take whatever f1 was because it's better and set it equal to whatever the x0 is, which then continues to update this loop. I'm using deep copy to copy the list basically because it's an object. I'm copying the object. But anyway, that's the gist of how this works. So before we run this, we need to set what these two methods will be. So let's work on the step method first. So function to step randomly in hyperparameter space. Let's go def step params. So the way this is going to work is this is our kind of test point, right? Let's just write that down there. Step x0. X0, and then we're going to step. So what we're going to do first is updated params. We're going to copy the input parameters. And that's just because this is an object and we don't want to modify the original object. We want to make a new copy and return it. Next, what we're going to do is selected variable. So what we're going to do is randomly select the variable we're going to perturb. So that's one of the order parameters or the trend parameters, right? Okay, so just to show you how this works, it's going to randomly select a variable and return it. So you see it's kind of selecting different variables as I keep rerunning it. It's exactly the behavior we want, which is perfect. Now, current value of the variable is just going to be updated params selected variable. That gives us the current value. Now what we want to do is update the current value randomly. So updated value is going to be current value plus. Now what I'm going to do is add a random -1 or 1 to the current value. So you could turn a P of 1 into 2 or turn it into 0. You could turn a D into 0 or you can turn it into 2. But now, what becomes important now is we need limits on these variables. They can't just be anything. So enforce parameter limits. So let's see. So I think that if selected variable is either P or Q, we're going to say the low and the high are 0 to 6. And otherwise, low and high is 0 to 1. So the P can be long, the Q can be long. D should only ever be 0 or 1. This is the differencing parameter. You never want to difference something more than once. Usually you just difference it once. Likewise over here, the seasonal parameter, you're usually seasonally dependent on the prior year, not on the prior 2 years. I mean, you could be, but to keep things simple, this capital P and capital Q are going to max out at 1. And D again should just be like this one, 0 or 1. The A0 or A1, those are actually Boolean sort of indicator. They should be 0 to indicate there or not there, so present or not present. So these are 0 or 1 also. So what we're doing now is just basically randomly selecting one of the variables, we're perturbing it, and we're making sure it stays between the limits, and then we're going to return the updated. Let me finish making sure it stays within the limits. So the way we could do that is the updated value. We have to basically sandwich it. So minimum of the low updated value. Okay, so what this does is it basically says if the updated value is smaller than the min, we take the min. Actually, I'm sorry. This will keep us essentially. I did it backwards. Sorry. This should be max. So if the updated value is larger than the low, we take the updated value. If the updated value is smaller than the low, we take the low because it's going to be the maximum, and therefore we never get a value under the low. And likewise, we're going to sandwich this in a min, a high, which basically says, we're either going to take the high or something smaller than it. We're never going to take anything larger than high. So that's exactly what we want. And just to show you guys that this does work, I'm just going to do it over here. So let's just say, call this value. Low is 10, high is 20, value is 15. This just passes through. What if it's 5? You get 10. So it thresholds it. What if it's 25? You get 20. So this is working correctly. Perfect. So we're going to come back here and finish this here. So the final updated params selected variable is updated value. And then we're going to return updated params. So essentially what we're doing is randomly selecting a variable, getting the current value, altering the current value, making sure the current value stays within limits, and then setting that new value and returning it. So if I came here and let's say I did for I in range 10, let's say I perturbed the original value a bunch of times, you're going to see, yes, the p-value got changed randomly. D-value got changed. These guys didn't get touched. The A0 got changed. If I ran it for more times, you would see more changes, obviously. So here the D got changed, the Q got changed, and so on. So this is working as intended. I see all the variables do flip at some point. So that's exactly what I expected. Perfect. So that's our step function. Our step function is working there. Now we need the score function. So the score function needs to return something that this loop understands and can kind of continuously select better and better scores. So let's go over here and start writing that. Function to score hyperparameter set def score and so it's going to depend on whatever parameters we set at that time and also on the data itself. So the way I want to do this part is let's grab this stuff here, copy. Actually, let's grab all of this and build off this. Okay, so indenting, right? Okay, so basically, we're going to build a model based on the input data over here, and we needed to get the parameters from there. So we got params p, params d, params q. And here, this is going to be params a0, params a1, and likewise over here, params capital P, params capital D, params capital Q. Now params feeds into this model creation, data feeds into it, awesome. And now this time we need to evaluate, right? So we need to compute error metric and return. But what exactly is going to be the error metric? So here we don't have the test set because we're trying to build a model. We only have access to the training data that's passed in. So what we need to do actually is create validation steps. So what this is how many data points at the tail end of the training data are we going to reserve as a validation set? So kind of like a test set. So I'm going to set it to 3, and then I'm going to say training set length is going to be data shape. So the number of rows minus the validation steps. So if we have 20 samples, the 18, 19, and 20, that last 3 is going to be in the validation set. The rest are going to be in the training set. So this model needs to be fit on the training set. So we take the head, so the beginning part, fit on that. And then with forecast, well, we're going to forecast the validation steps. And the exogenous regressor is going to be, again, GDP from the data, but it's going to be the tail end of the validation steps. So now this gives us a forecast that works in here. And let's go ahead and return that. So let's just see what it looks like. And let's get our dummy parameter here. X0, df train. X0 is what we're using down here. So let's see what this looks like. So we get the validation set is 3. We get 3 variables being forecasted, 3 time steps. Let's do 5. Now we get 5 time steps being forecasted. So again, this is the tail of 5. And actually, let's grab the actuals, which would be data, sales, tail, validation steps. Let's return actuals. Now you see you get the predicted and the actuals next to each other. And then from there, you want to compute an error metric. It's kind of very simple. All we'd have to do is say error is going to be forecast minus actuals. And then we do absolute value, and then we take a mean. And then we can return the error. And we say we get an error metric, which is exactly what we need. Now, this would be fine, except I personally, I like to kind of make this flex because I've seen overfitting happen for a fixed value of this. So what I mean by that is like if you do one step ahead cross validation, your model might just get good at predicting that one kind of structure in the series. But if you alter this to be like, one step ahead, 2 steps ahead, 3 steps ahead, 4 and 5, and so on, and you evaluate the model on average across all those steps ahead forecasts, that actually is a more robust way to kind of evaluate the model. So that's what I usually do. So I'm going to do that here. So what I'm going to do is say 4 validation steps in this sequence. Do all of this. So do all of this, repeat this for different validation step lengths, and we want to always be calculating the error. And the way I'm going to actually calculate the error is I'm going to take the last kind of time point here. So what I mean by that is if we're going to predict a series that has, say, 20 samples, and the validation set is samples like 18, 19, 20, right? For 3 step ahead, we want that 20th sample, the error on the 20th sample. For 2 step ahead, we want the error on the 19th sample. And for 1 step ahead, we want the error on the 18th sample. So the way we're always going to get that is basically by doing this. Forecast tail 1. Give me the last value of the forecast, whatever the validation steps are, 1, 2, 3, 4, 5. Give me the last one. So the first, the second, the third, the fourth, or the fifth, whatever it is. And the actuals, give me the same thing. Give me the last value. And what I'm interested in is the difference between those, between these two, the last ones. And I'm doing that for all the validation steps. So I'm getting the 1 step ahead error, the 2nd step ahead error, third, fourth, and 5th step ahead error. And what I want to do actually is accumulate these in a list. So every time I compute one, I want to accumulate it. And I don't want to return error. I want to return the average of all of them. So that gives me a more robust way of doing it. Nothing fancy going on here. I'm just kind of cross-validating over that, so I'm not so dependent on one cut of the data. So let's go ahead and run this. I get a different value. If you remember, the previous value was a 0.9. It's similar here, so that's cool. So I think I'm good with that now. Hop back down here to our hyperparameter optimization search. So what we're going to do from here is actually look at this. So let's print out progress. So let's do print current score. Now let's do this, F naught. And let's see what this looks like. So I initialize an initial score. I forgot the train here, my bad. So print initial parameter, F naught. So we're at about 0.9. That's the initial parameter score for this initial guess. We're going to come here and we're going to make these steps and we're going to get a new score. We're going to keep trying to update the score and let's sort of see how this works. And then here for score, I need training data in there. So let's see what this does. You can see we're at 90. It found a better score, it dropped to 0.7. It's staying steady at 7. So every time it goes a line, it's mutating the variable. Oh, it just found another one. It dropped to 0.6. Let's keep going. 0.6. Let's see if it finds a better solution. Possibly got stuck in the parameter space. We'll see. Okay. So we're not finding a new value, although it's continuously going. We're kind of stuck at the 0.66. See if it finds something else. And in the meantime, let me actually grab the plotting. I want to copy this because what I want to do at the end, what I want to do down here to actually visualize the best fitting parameter set here. So what I'm going to do is, let's say x best is deep copy of x0. Because x0 is what's getting updated in this optimization loop. And you can see it's still stuck, which is interesting. So I think it finished. Let's do x best here. So this is the last one that it found. And let's see how good this one is. So I'm going to do, yeah, this is good. Here we have to replace this with x best p, x best d, x best q. Here we got x best a0, x best a1, and the seasonal parameters, capital P, T, Q. Okay. Let's see how this guy looks. Okay, so it doesn't really look too great, but it looks interesting. It's kind of in the same ballpark region, but you can see it's taking off, so that's interesting. Let's go back up here and let's grab this. What I want to do this time is actually, when the loop ends, I want to make the x best equal to that. And actually, so we saw something interesting here. You can see it kind of got stuck, right? It went down from 0.9 to 0.7 to 0.66, and then it was just kind of stuck there forever. It wasn't changing. So why is that happening? Well, if you look back at this code, we can only go downhill. We can only accept improved moves if f1 is smaller than f0. So if our step is somehow leading to lower scores, which sounds like we want to always do that. However, we don't always want to keep going downhill because then we get stuck. We get stuck in local minima, basically. So the way to avoid that is to sometimes go uphill. Sometimes is the key word. So the way we're going to do that is we're going to add a clause here, else. So now, if new point is worse, except with some probability. Now, if I'm going to write this and I'll explain what it is. So you generate a random number, and if that random number is less than this quantity, then you will go ahead and accept the move, even though it is a worse move. So you accept the move even though it's a worse move. Now, what is this? What is going on here? Let me set temperature. So what this is actually some method from statistical physics. This is like the Boltzmann constant. You see it a lot in like the way they search their hyperparameters for like protein folding and stuff like that. But this is basically a delta of energy over a temperature. But the point of this whole expression is to say, if it turns out that the difference between the two scores is small relative to this normalization temperature value, so, if it's small enough, then 2 raised to the negative power of the small number, it has a reasonable chance that you can generate a random number smaller than it. So, in other words, if these two values were equal, this would be 0. Whole thing would be 0, and it would be 2 raised to the 0 power, which is 1. And so when you generate this random number, it's always going to be smaller than 1, so you're going to accept this move. However, if f1 was very much larger than f0, that means this is a big number, and therefore this is still a big number, and it's negative. So what ends up happening is this value becomes small. It may become, instead of being 1 when they're both equal, maybe it drops to like 0.1. And now you have a worse chance of getting a random number of 0.1 or smaller. So you'll accept this move with less probability. So this basically controls that. For worse moves, you have lower likelihood of moving there. For moves that are not so terrible, you have a higher chance of moving to it. So this allows you to kind of not get stuck. So I'm going to show you how that looks here, basically. So let's just do some bookkeeping here. So let's keep track of best parameters. So let's track. You got X best, and let's take the best so far. So after this initialization, this is the best. And then over here, what we're going to do is say update the best parameters. So if f naught is less than f best, then what we're going to do is say f best is f naught, next best is x naught. And then we can actually print out the best score alongside the current score. And this we no longer need because we're going to have x best being tracked. And that's already reflected here. And the only other thing we need here is I want to make a chart of the steps. So to show you guys, so optimization progress, let's say current score and f best score. So we're just going to keep track of this f naught, and then we're going to do f best. Okay. So these are going to keep track of that. And then I come down here, I'm just going to do a QT figure plot f naught on. This is the current probe value, and then we're going to plot f best, and this is like the total best parameter. Okay, so legend show. Let's see what this looks like now. Let's run this. Okay, and let's go ahead and run, and let's change this a bit. So let's just p1d, so 0 0 0 1. Let's call this 1. Let's see, so 0.6. Now let's run this guy. You can see we're at 1.6, 1.6. We got a better score. We drop down. We're at 1.45. So we're still going. As you can see, we're still kind of stuck at this 1.45 number. We got 1.43, which is cool. See, we went up there, 1.4 to 1.5. We accepted a bad move, so we went uphill. But our best score is still 1.43. We just went uphill again. And then we went back down. We dropped all the way to 0.7. So you see how we went up in score. The score got worse, but then it got way better. We dropped all the way to 0.7, which is pretty awesome. Now we're at 0.5, which is even better. So whereas before we got stuck at 0.6, this time we were allowed to take downhill moves, and when we did get stuck, we were able to go back uphill. That prevented us from getting stuck. So we were allowed to explore the parameter space in much higher degree, much better degree. So that's why we were able to do this. So let's see. It looks like we went uphill a little bit. Went uphill. We're still going. Okay, just waiting for it. I had put 100 optimization steps. So we started at 1.6 and we went down. We're all the way down at 0.52, and the path was not, steady. When this is done running, I'll run this command and I'll show you kind of the ups and downs to this thing, kind of make it visual. Okay, so now it's done. Let's run this. Let's actually give that a bigger fig size. You can see the blue line is the current probe. The orange line is the best probe so far. So you can see it was flat. The score got worse, and then it found a good solution, went down, and then they both went down, and then they got stuck, and then the current probe was allowed to get worse and worse and worse, but then it got unstuck, right? It got unstuck, and then it found a huge solution to come down, and then they both came down again, and then they're kind of stuck. The blue goes back up, it comes back down. So that's how this kind of curve will generally look. So let's see. I rerun this now with the best parameters from that optimization run. You can see how good it looks. I mean, your green curve, so using only the blue data, we were able to predict the green curve, which is very much on top of the orange curve. Obviously, it's not perfect, but the forecast looks pretty good, especially for a series like this. I mean, you're talking about a very, it looks kind of steady here, and then it just experiences a huge perturbation because of COVID, and then it gets erratic after. It's sort of still somewhat decreasing, but it's like up and down and stuff. So the fact that we're able to predict something reasonably well, given it how erratic it is and how much it's affected by the market and everything, is pretty remarkable. And I think that's kind of thanks to the method behind all of this that I kind of walked you guys through. But this is sort of like the crux of the whole thing. So by following this procedure, by cross validating correctly, making sure we're not biasing in any direction, doing a good search of the parameter space, we're able to come up with a model that mimics the data generation process as closely as possible, and we're able to get a pretty decent forecast. Now you may be asking, why didn't I? Why did I do all this, and why didn't I just do an exhaustive search? Well, you're welcome to try that. And I guarantee you that if you did try that, you'd be waiting for hours, days, maybe multiple days for it to even converge. And doing it this way, we were able to efficiently search the space more with like a randomized way, with far fewer steps. So it was much more efficient. We were able to arrive at a good solution much more quickly. I actually had tinkered around with doing the exhaustive search, which I didn't show here. And I was like, I'm not doing that because I was literally waiting for hours for it to just get to any reasonable extent. So the reason is you've got a lot of combinations here. So, right, you got this might have 7 options. This has 2. This has 7. This has 2, 2, 2, 2, 2. So it's like a combinatorial explosion, right? So you got, on the P, you got 7, then you got 2 for the D, another 7 for the Q, and then for the capital PDQ, you got 2, 2, 2, and then for the A0, A1, you got another 2 and 2. So that's, about 3,000, which doesn't seem like it's a lot. However, if your function evaluation on that is time consuming, then this is a big number. It can be a big number if every one of those 3,000 takes a few seconds to run. Um, so, like, I don't know, let's just say, what if it took 5 seconds to run? You're looking at this many seconds, and divide that by 3,600. You're looking at 4.5 hours. So to do exhaustive search, it may take like 4.5 hours, right? So you could definitely leave a job running overnight, but this is just a much more efficient way to search large parameter spaces. So that's kind of the whole deal there. So that's it in a nutshell. We were able to, come over here, pretend like this is the future, and we were able to come down here using our method and actually do a good job at predicting it. So hope you enjoyed the video. If you have any other time series forecasting problems you want to throw in the comments for me to tackle or do a demo of, I'm welcome to. It's pretty fun for me. I do this all the time at work, and this method I've outlined has been extremely successful in all the jobs that I've had. Um, so it's really good to understand how to properly cross validate these time series models, and how to kind of make them work in practice with all the data cleanup, which was another thing. Making sure I brought in data from different sources and collapsed them down into a consistent monthly grain. That was the whole, piece of work in and of itself. So, very interesting stuff. One thing also that I'd kind of touch on is I actually, for my real life forecasting, I actually use R. R has this package called Profit. I'm sorry, no, well, it has Profit, so does Python, but it has a package called Forecast. Forecast is a pretty nice package. It has an easy interface into neural network models, autoregressive neural network models, all kinds of ARIMA models, exponential smoothing models. And then I also bring in Profit into the mix. And so what I end up doing with the R package, the forecast package in R and the Profit package together, is I basically come up with a bunch of time series models, and I cross validate all of them, and then at the end I take an average of all of them, and that has proven to be extremely successful in like all the projects I've been working on. And I wish I could show that approach. Maybe one day I will over YouTube, but it would take so long. That demo would take forever because it's really really involved. This was like a lightweight version that explained many of the core concepts I use, which still works pretty well. And you can implement something similar in Python, like what I described in R, but that's for another day. But hopefully, this was helpful to you guys, and I'll see you next.